Hey guys, and welcome back to another YouTube video. In today's video, I'm going to be teaching you how you can create a 97% accurate neural network in Python, which can classify horses and humans. And by the end, you will have created something like this. So this guy is, I guess, a bit less accurate. I don't exactly remember. Um, you can see it and predict the things. Now you might be wondering that why these are black and white images. That's because I did that. I used some extra code like over here to convert them. You could go ahead and convert them to a colored image, but I don't want to do that because I just feel the model will become a bit difficult to process, and I don't want to do that to hinder the performance of the model. So first, what I did was I just loaded in all of the data that I needed. Then what I did was I collected some information on the data. So instead of just going over here and manually searching for that, there's a pretty cool thing by in TFDS or TensorFlow datasets that you can just make a variable and then just type of tfds.builder and then just put the name of the dataset that you're going to be working on. Then you just do builder.info and print out the info and you will get it. Then what I did was I really quickly you need like now you can also copy this code in your Google Colab and you'll have this. So this is like just me teaching you how to do that. Obviously coding part should be done by yourself. So then what I did was I just took all of the data and you need to split it into a DS train and DS test, which stands for dataset train and dataset test, and it should be split into the training data and the testing data. So what it does, it makes the train images, train labels, test images, test labels, and we are going to be using the horses and humans, so that's why. This piece of code is just used if you want to look at some examples. So like on running this, you will see it shows us some examples. So like this guy. What the cool thing is, to see some examples, you can also go ahead and see some test examples, and it won't actually hinder the performance of the model. So that's pretty good. So you can see the first horse and the humans over here. But I'm just gonna keep it as train for now because I don't think we need. It's important for us to look at the test examples. Then what we need to do is we need to convert these to a numpy array, and we also need to convert this to the black and white type of image. The reason why we do that is because according to me, when you are classifying a horse or a human, color is surely important, like it's very important. But according to me, the thing that's a bit more important than color is the shapes. Is because you would see that a horse has its head projecting outwards from its body, so it's like kind of long neck, while a human has the head that's projecting in the northern like upwards with it, and the neck is pretty short. So we could do this pretty nicely with some convolutions, but it could also lead to a hindering in the model. So and also for not a, this is not a super big data set, so I decided to not put in convolutions. You could obviously use some max pooling, use some convolutions in this, but I decided to not do that. So this is just a little list comprehension that I did twice, just to convert it, all of the training and the testing data into NVDA. Then what do I do is the when we convert this, it becomes an int. So then we make it a float 32. The reason being we need to now divide it by 255 for pound in RGB scale. It's like by 255. Then I just specify the class names for the model, which is either a horse or a human. Then I went ahead and made the model. In today's video, I will also, I think, I will also teach you how you can make such great like this model. Like how do you come up with the amount of nodes that you want. As you can see, it's pretty, I would say, good. Like I went 900, 800, 600, and then 2, which I will explain. Then I just quickly compile the model with an Adam optimizer and a sparse categorical cross entropy loss. In the most cases, you are going to be using this as the same, the compilation code. The change is going to be in the model and the fit and the batch sizes and all of that. The reason why all of this is going to be the same, usually it's either sparse categorical cross entropy or binary cross entropy. You won't actually be using categorical cross entropy a lot of times, but it's obviously depending on your data. Metric says accuracy, that's kind of optional. If you just go with the laws, you can kind of get the accuracy also. Then I just fit the model with a 25 epoch for time and a 32 batch size. Batch size, as I had explained in the previous videos, are the amount of images that we show in one epoch or one iteration. You could go with a higher batch size or lower batch size, but 32 worked really well for me, and I feel like it also made the unit work like not that slow, and yeah, it like the one epoch runs in like a second, or even a second. Then I just made it a prediction variable which would predict the test images, and then I just used some. Then what I did was I reshaped them into a 300 by 300. The reason that was is because I think all of these, the shape we were getting was pretty weird. It was like 300 by 300 by 1. Because of that, what was happening is it would throw me an error, and if I would even try to find a way around it, it would become like a scalar value, and it needed to be converted to a scalar index, which even though I did, it would still not work by using np.ascalar. So then I just made an X label that would tell me the action and the title that would be the prediction. And there we go. You have your model. Uh, Now all of the model making things now side. How did I come up with this thing? Now the first thing, usually we just flatten all of the things just to make it a bit good in the shape, which I won't talk about because I've already talked about. All of these dense layers are what I'm gonna pay a lot of attention to. So you could see the first dense layer that I made was one with the maximum amount of nodes or neurons. The reason why I did this is because usually the data that we're gonna get in the first part, like the it's going to be the direct input, like it's going to be what like we as programmers feed it after doing all of this cleaning up. So that is going to be requiring the most amount of I would say great deal of looking at. And then what we do is we feed it the maximum amount of nodes. So what 900 nodes, it was not arbitrary. I played around with it. So I went with like something like 550. Then I went with 700. Then I thought that I think like and then I also went with something like 1,500. And all of that did not work. So then I came to this number like a 900. Like obviously you're gonna be needing to play around with it. So that's why I put a 900 amount of nodes. So what had happened was the data that we got was cleaned up really nicely. So the data that we need to pass it through another really good filter. The reason why I just decreased 100 nodes from that is because usually the first layer cannot do a lot of processing and classification and actually the neural network stuff. It's because the data that it has got is like the raw data. So what that can so a lot of computation is required after that, so that's why. So then I just made it's just 100 neurons less. Then I just made a bit that was like just 200 neurons less. So what happened was the amount of nodes became 2300, and I feel like that number was pretty good. So it really made all of the things cleaned up really nicely. Obviously it's not a 100% accurate, but it's pretty accurate. Like it's really accurate, and I feel like it's really good. And now, if you don't know a lot of about neural networking, you might be saying why I made in another dense layer with only two nodes. Like I could have just not put it over there, or I could have put 602 over here. The reason why that is because whenever you are working with a neural network, the when you have made the entire model, you need to make an output layer. So the layer that will actually take all of the process data and will feed it to the as the output, which will be fed in over here and shown. So it's not a flattened layer. Like a flattened layer is usually the first layer that we put. It's a dense layer, but the dense layer in the amount of nodes that are put in the dense layer have to be equal to the class names or the possible predictions that the model can make. So that's how it works. And usually even the activation is different because the rectified linear unit is usually used for prediction and softmax is usually used for shoving the images and showing the output. So that's why. I feel like I would have butchered the explanation a bit, but I feel like you understood this quite a bit. Obviously, if you're going to be working with a pretty large data set, you're going to be increasing the nodes over here. You're going to be adding a ton of more dense layers and convolutions. Obviously, can make a really successful neural network without a lot of convolutions. Still, that's right. So, let me just have a quick check at the recording. Alright. So, this is the entire neural network. Um, Obviously, the link will be in the description of the video, so you guys can go ahead and mess with all of this data. And yeah, so if you want to know more about some these things that I've done over like NumPy and all of that, comment down below and I will try my best to like I think make a little video on NumPy, some basic NumPy commands, and comment down below if you want to see some more other types of neural networks like audio classification. I won't come up with that pretty soon because I just have got a really good heads up right now about audio classification that NVIDIA has got this Nemo thing, which is pretty good. I was trying it a bit, so I won't be publishing any audio classification videos these days because I am trying to work with that and hoping if I can get it functioning pretty quickly, then I can make a video on how to use that, and it's pretty cool and one of the latest technologies. So that is it for this video. If you like this, please subscribe to the channel. The reason why I'm posting a lot of neural network stuff and not a lot of my Pygame series, I don't even know if I'm not gonna continue that because it's just that these days I don't have a lot of time to just sit down and make a game. I really am working on a lot of machine learning things, so that's why I don't even know if we are working with the Pygame series. Don't you worry. I'll probably do a live stream on YouTube sometime soon. I will just make or you can actually, you know what, you can look at my Aga.io video. It's like you can follow along with that and make such a great thing. So you probably will have a finished project. So don't you worry. And also the game that I chosen was pretty complicated. I figured it out after making the video. So yeah. So, and if you also don't understand all of this complex math, don't you worry. Comment down below. I will make a video on how does the math in neural networking work. Or if you still don't understand, don't worry. You can um, comment down below, and I will like make a little ML tutorial series on linear regression and really basic topics like that. Because neural network is not that basic. So that's it for today, guys. I hope you enjoyed the video. If you did, like and subscribe to the channel. It's a great help to me. And until the next time we meet, bye bye.